Hello. So in this video, we're going to be talking about continuity. Historically, like in your pre-calc classes, you have defined continuity in this sort of hand-wavy kind of way, where a graph or a curve is continuous, right? If you can sort of draw it in this nice smooth way without picking up your marker, pencil, whatever, right? So we'd say this thing is continuous because I could draw it without picking up my pencil. But as we're sort of moving forward, right, in calculus, one of our goals is to try to make these sorts of things more rigorous, and continuity is one of these things. The problem that we're going to run into sort of inherently with continuity is that we talk about continuity at a point, right? So if we want to talk about, so pick a point here, so let's say this point here. If we want to think about this point here and talk about whether or not this thing is continuous, this is sort of a weird thing to say because, as mentioned, right, we envision continuity as this drawing of a line, and a point is not a line, right? So the way we sort of need to work with this when we try to make this a more algebraic process is that we want to think about the point, but we also kind of need some information about this little section of the curve nearby, right? But again, we're worried about sort of the point, the kind of tiny little bit here, which means we want as small a region around it as possible. So hopefully by this point, as we think about getting closer and closer regions around a point, this should have a haunting familiarity with limits, right? So this is where we are going to need this limit, is the idea of getting really close to a point, but also sort of continuing, considering the area sort of right nearby the point. So now that we have limits, we can actually define continuity in a way using limits that is algebraic. So that's what we're going to be doing next. Okay, so when we are going to talk about continuity, like we were saying, we want to talk about continuity using the framework of limits, right? So we can get the little bit of information around. A lot of the times, a lot of textbooks, and if you look up sort of the definition of continuity with limits, you get this very compact single statement, which sort of obscures what's happening a little. So what I'm going to do is I'm going to present this as sort of the three rules that one statement that is usually found, which is covered in our text as well, is going to sort of really say the three different parts. So if we have sort of starting with our bit of continuous line here, right? Nice, solid, draw it without picking up a pencil. We're going to be thinking about continuities by thinking about discontinuities, right? So again, in pre-calc, covered discontinuities. First type that we sort of usually think about when we think about continuities and discontinuities is this jump discontinuity, right? This piece where we're going from this top line here down to the bottom line here. So we want to, right, avoid the discontinuities, right? That's what we're trying to do here, define something to make it continuous. So we need some way of making sure this doesn't happen, right? So this is actually the first place where our limits are going to come in. So if you remember when we talked about limits, we talked about how a limit exists if the left and right limits exist and agree, right? They're the same thing. So if we think about limits in this context, right, as we're coming sort of across from the left along this nice flat line, we get something closer to 5. But if we're coming sort of up this curve from the right, we're getting something closer to 3. So the left limit here is going to be that 5. The right limit is 3. They're not the same thing, right? So if the left and right limits aren't agreeing, it's because we're sort of going to different places. And as a result, this is not a continuous point, right? We have this jump discontinuity. So the very first thing that we need, right, is for this limit at the point that we're looking at, we need this limit to exist. And really what we're saying is that we need the piece from the left and the piece from the right to go to the same spot, right? The next kind of discontinuity that we usually talk about is that whole discontinuity, right? So if we have a curve coming and it just sort of continues to go through, but it doesn't actually have that point, right? This B here is an open circle, so it doesn't have that value there. This is also discontinuous, right? This is the whole discontinuity. But our previous bit, right, this limit of the x value existing, well, that limit does exist, right? Because from the left it's going to 0, from the right it's coming down to 0. So the limit definitely exists, but nonetheless it's discontinuous. So this is where the second rule comes in. So remember that the whole discontinuity occurs because we have a domain restriction, right? We're just straight up missing that point. So second part is the function at that x value needs to exist, right? So this isn't a limit directly, but we need that the function is defined at the point, otherwise we're missing it, so it makes no sense to talk about that point. But as pointed out here at our C point, right, we have the limit existing, again, still coming to the same value on both sides. The function exists, right? It's way up here, though. So not only do we need the function to exist, but we also need the function to be in the right spot, right? We need that point to be where it needs to be to make this thing a nice continuous curve. So we need that the limit exists so that we have sort of everything but the dot. We need the function to exist, but we also need that the function's value and the limit app value are the same thing. And this is that magic phrase that occurs, right? That if you look it up, it says like it's continuous if the function's value is the limit's value. But in order for that statement to make any sense, you kind of need those things to both exist. And in fact, their existence is sort of important for its own sake, right? So the limit existing is how you avoid the jump discontinuity as well as the asymptotic or infinite discontinuity, if you remember that. And then the fact that the point exists isn't quite enough. We need it to also be in the right spot, right? We certainly need it to exist according to B, but we need it to be in the right spot. Okay? So those are the three rules you want to think of when you're thinking of continuity in this more algebraic way, not just the without picking up your pencil version. Recall that when we say a function f of x is continuous at a point x naught, we are really saying three different things. That the limit at x naught exists, that the function is defined at x naught, and that f of x naught equals the limit at x naught. Each of these three conditions is designed to avoid a discontinuity. In particular, the first condition, that the limit exists, is designed to avoid most of the discontinuities we intuitively think of when we think of discontinuities. Remember that a limit existing means that the left and right limits must exist and equal each other, which means that as you follow the curve toward x naught from the right and the left, we must eventually get infinitely close to the same y value. This is another way of saying that the curve must go to the same y value, say L, at x naught, which means that the curve must approach the point x naught, L. But remember that the limit itself doesn't tell us anything about the function's value at x naught, or indeed if the function is even defined there. Our next condition handles the concern of whether or not the function actually exists at x naught. In particular, condition 2 just demands outright that the function exists at x naught. Granted, this is a little heavy-handed, but it works. Kind of. Even though this tells us the function exists, it doesn't tell us what the function's actual value is. This is where a third condition comes in. Our second condition forced f of x naught to exist, but that isn't enough to know that it fills in the circle which represents our limit's value at x naught. Our third condition requires that f of x naught has the same value as the limit. This forces the dot representing our function's value at x naught to be in the right spot, to ensure that we don't have an open circle with the dot somewhere else. Rather, the dot fills in the open circle we were worried about. Thus, we are left with a nice continuous segment of the function. So, we can see that we need all three conditions: that the limit exists at the value of interest, that the function exists at the value of interest, and that the limit and function have the same value. Rather than saying that the limit and function have the same value, mathematicians will often say that they agree at the point of interest. But the important thing to take away here is that if you're missing any of these conditions, then you may not be continuous. Okay, so as we've seen, now that we're trying to introduce this idea of having a more sort of analytic approach to continuity, we are going to want to try to think of continuity now, not necessarily in the sort of drawing without picking up your pencil. This is a good sort of intuitive idea. But now when we think of continuity, we want to think of these three rules, right? So the first one, this idea that the limit at the x value has to exist. This will allow us to avoid things like jump discontinuities like we saw in infinite discontinuities. The second thing, right, we need the function to exist, and this is sort of inherent in the problem that limits don't care at the, of the function's actual value at the point, as we've discussed before. So since the limit doesn't tell us that, we need to know that the function does exist. And the sort of third catch-all, this one that is often sort of boiled down to, but really inherently needs the other ones to work, this idea that these things are equal, right? That the point is where we need it to fill any kind of whole discontinuity. It's also worth sort of thinking about, and we will see this in future example videos and things, that this works the other direction, right? So for continuity, we've been talking about how to tell if something is continuous, but if we already know the thing is continuous, then we already know these three things work, right? And this is actually pretty helpful because it will tell us things like the limit already exists, we don't have to worry about whether or not it exists. And moreover, that we can evaluate things at limits by just plugging in the value because, according to our third point here, we know these things are equal. So we'll see this in other videos, examples, and things, but start sort of grinding gears, right? Thinking about other ways you might use this, not just to show something is continuous, but how continuity might work for you.